Hello viewers, welcome to my YouTube Anjaneya Math channel. In today's class, we are going to study the elementary transformation of a matrix. Before considering the elementary transformation of a matrix, let us revise the definition of a matrix. So we know that a matrix is an arrangement of numbers in rows and columns enclosed by a bracket. The numbers which are placed in a horizontal way, that is to be considered as the row of a matrix, and the numbers which are placed in a vertical way, that is to be considered as the column of a matrix. The matrix is usually denoted by the capital letter. Say for example, the numbers 1, 2, 3, 4. Some numbers are placed in a horizontal way, some numbers are placed in a vertical way. So the numbers 1, 2 are placed in a horizontal way. This is to be considered as the first row. The numbers 3, 4 are placed in a second horizontal way. This is to be considered as the second row. The numbers 1, 3 are placed in the first vertical way. So this is the first column. The numbers 2, 4 are placed in the second vertical way. So this is to be considered as the second column. And these arrangements are enclosed by either an ordinary bracket or a square bracket. So let us enclose these arrangements of numbers in a square bracket. The matrix is usually denoted by the capital letters. Say A. A is a matrix consisting of the elements 1, 2, 3, 4. By observing the rows and columns of a matrix, one can state the order of a matrix. As this matrix consisting of 2 rows and 2 columns, the order of a matrix is denoted by 2 by 2. Here first suffix denotes the number of rows, and the second suffix represents the number of columns. First number gives the total number of rows present in this matrix. Second number gives the total number of columns present in this matrix. So if the matrix consisting of same number of rows and same number of columns in a matrix, or a matrix having the number of rows is equal to the number of columns, then that matrix is known as a square matrix. So A is a square matrix. The matrix is consisting of 2 rows and 2 columns. Therefore, this matrix is to be considered as a square matrix. Let us consider the elementary transformation of a matrix. So let us first understand what is the meaning and the application of elementary transformation of a matrix. So let us first understand the meaning of the elementary transformation of a matrix or the applications of the elementary transformation. The elementary transformation of a matrix are 6 operations. The 3 operations are related to the rows, and the remaining 3 operations are related to the columns. Now let us understand what are those 6 operations. So let us consider the first. Interchange of any 2 rows or any 2 columns of a matrix. If ith row and jth row of a matrix are interchanged, after interchanging, the original matrix is transformed into the new matrix. Say if ith row and jth row of a matrix are interchanged, then its transformation is represented by the notation. Ith row Ri, jth row Rj. Here R stands for what? Row. So the interchanging of two rows is represented by the symbol double-sided arrow mark. What is the meaning of this? The ith row and jth row of a same matrix are interchanged, or it is also denoted by this symbol Ric. This is in case of what? Row. If it is in case of columns, if ith column and jth column of a matrix are interchanged, then its transformation is denoted by Ci double-sided arrow marker Cj. Means what? Interchanging of the ith column and jth column of a matrix. Take one example. A is a matrix having the elements 1, 2, 3, 4. Let us perform the row operation, say R1 interchange R2. So after performing this operation, the new matrix which we will get is, in place of first row you have to replace the second row, and in place of second row you have to replace the first row. That means the first row becomes the second row, that is 3, 4, and second row becomes the first row, say 1, 2. So this is the meaning of the operation R1 interchange R2. That means you have to interchange the elements of first row with the second row, and it's a vice versa. Now if you see this matrix 3, 4, 1, 2 is not equal to the original matrix. So definitely matrix A is not equal to what? 3, 4, 1, 2. But we can say that A is equivalent to, this symbol indicates what? Equivalent. So the meaning of this symbol is what? Equivalent. So A is equivalent to the new matrix 3, 4, 1, 2. The new matrix which we got, of course it is not equal to the given matrix. It is not equal to the original matrix. But this matrix is equivalent to the original matrix. So this is in case of what? The row transformation. Suppose if you perform the column transformation, say the meaning of C1 interchange C2 is nothing but what? Interchanging of the elements of first column and the second column. So from the given matrix A, you would replace the first column as what? Second column, say 2, 4. And the second column becomes what? The first column, 1, 3. Definitely this matrix is not equal to what? The given matrix A. But we can say that this matrix is equivalent to the given matrix. So 2, 1, 4, 3. Given matrix A is equivalent to the new matrix which we have written here by performing the column operation. So this is in case of the interchanging of any two rows of a matrix or interchanging of any two columns of a matrix. So we have seen the two operations here. One is in case of row, another is in case of what? Columns. Then the next operation is what? Multiplication of the elements of any row or any column by a non-zero scalar. Scalar means what? Any constant, non-zero constant number. K is any scalar. And if I consider the ith row, then each element of the ith row is multiplied by a constant K. This transformation can be represented by K into Ri. Means each element of the ith row is multiplied by what? A constant K. Say for example, A is a matrix having the elements 1, 2, minus 3, 0. And if I consider the constant scalar as say minus 2. Now let us multiply this constant K to each element of the first row. Then that can be represented by what? Minus 2 into R1. Means the new matrix which is obtained by multiplying each element of the first row by what? The scalar, the constant minus 2. So that means the first row can be written as minus 2 into 1. Then second element is what? Minus 2 into 2. Whereas the second row will remain as it is. Minus 3, 0. So further it can be written as, so minus 2, minus 4, minus 3, 0. So this is the new matrix which is obtained by performing the row operation by multiplying each element of the first row by what? Minus 2. Whereas this matrix is not equal to what? The given matrix A, but it is equivalent to what? It is equivalent to the given matrix A. This is in case of what? The row operation. The same operation can be performed in case of the columns. Say for example, if I multiply say 3 to each element of the second column. Multiply the constant 3 to each element of the second column. Then the new matrix so formed is what? So there is no change in the first column. The first column will remain as it is, 1 minus 3. Whereas the second column is what? Which is obtained by multiplying the constant 3 to each element of the second column. Say 3 into 2. Then 3 into 0. Which can be further written as 1 minus 3. 3 2s are 6. 3 into 0 is what? 0. So this is the new matrix which is obtained by performing this column operation by multiplying each element of the second column by what? 3. Whereas this matrix is not equal to what? It is not equal to the original matrix. But the original matrix is equivalent to what? The new matrix which we have obtained here. Alright, this is the second operation, multiplication of the elements of any row or any column. Take the next operation as adding the scalar multiples of all the elements of any row or column to corresponding elements of any other row or any other column. What is the meaning of this? Suppose if k is a non-zero scalar, k is any constant, and the k multiples of the elements of ith row or ith column are to be added to the elements of jth row or jth column, then the transformation symbolically denoted as Rj tends to Rj plus k times Ri. This is in case of the row operation, or the same operation if you perform in columns can be written as Cj, jth column tends to jth column plus k into ith column. So what is the meaning of this? First, each element of the ith row are multiplied by the constant k, and the product is to be added to corresponding elements of a jth row. So this is the new jth row formed in a new matrix. Take one example, matrix A equal to 1, 2, 3, 4. Let us perform this row operation here. So R2 tends to R2 plus 2 times R1. That means the new matrix which we are going to write here. In that matrix, the elements of the second row are obtained by what? First we are going to multiply the constant 2 to each element of the first row, and the product is to be added to the corresponding elements of what? Second row. So say there is no change in the first row, will remain as it is. So second row plus 2 times first row, second row is here 3 plus as it is 2 is multiplied to the element of the first row, say 2 into 1. Similarly here 4 plus 2 is multiplied to the element of the first row, so 2 into 2, which is equivalent to first row as it is. So 3 plus 2 ones are 2, then 4 plus 2 twos are 4. So that is 1, 2, 3 plus 2 is 5, 4 plus 4 is what? 8. So this is in case of what? The row operation. So the meaning of this transformation is what? Like this. The same operation can be performed in terms of the columns also. Say the matrix is 1, 2, 3, 4. So according to this operation, there will be a change in the elements of, there will be change in the first column, whereas the second column will remain as it is. The second column is what? 2, 4, whereas the elements of first column are obtained by what? C1 means here 1 plus 2 into C2. C2 is here 2. Then C1 is here 3 plus 2 times C2. C2 is here 4. The second column as it is. So 1 plus 2 twos are 4. This 2 will remain as it is. 3 plus 2 fours are 8. 4 will remain as it is. So 1 plus 4 is 5. 2. 3 plus 8 is 11. 4. So this is the meaning of this column operation. Right? Now whatever the row operations and column operations we have seen just now, by using those operations we work out the examples based on those 6 operations. The question is like this: apply the given elementary transformation on the following matrices. So we are given one matrix here. So matrix A equal to 1, 0, minus 1, 3, and we are given the row operation R1 interchange R2. Solution: given matrix A equal to 1, 0, minus 1, 3. So we have to perform the row operation R1 interchange R2. R1 interchange R2. That means you have to take the interchange of the elements of first row and the second row. The second row becomes the first row, say minus 1, 3, and the first row becomes the second row, 1, 0. So this is the new matrix which is obtained by performing the row operation R1 interchange R2. The next example is matrix B equal to 1, minus 1, 3, 2, 5, 4. You are asked to perform the operation R1 tends to R1 minus R2. So the solution is like this: given matrix B equal to 1, minus 1, 3, 2, 5, 4. Consider the operation R1 tends to R1 minus R2. That means the new matrix which we are going to write here, in that matrix, the elements of the first row are obtained by performing this operation. So the elements of first row minus second row. Say the first element is here 1, minus first element of second row is 2. Next element of first row is here minus 1. Then minus next element of second row is here 5. Minus 1 minus 5. Next is what? 3 minus 4. Whereas there will be no change in the elements of second row. So no change in the second row. 2, 5, 4. B is equivalent to 1 minus 2 is minus 1. Minus 1 minus 5 is minus 6. 3 minus 4 is minus 1. So the second row will remain as it is. 2, 5, 4. So this is the matrix which is obtained by performing this row operation. Now the next example is matrix A equal to 5, 4, 1, 3. So you are asked to perform this column operation C1 interchange C2. So given matrix A equal to 5, 4, 1, 3, consider the column operation C1 interchange C2. So the new matrix A is obtained by interchanging the elements of first column and the second column. So the first column becomes the second column 4, 3, and second column becomes the first column. So 5, 1. So this is the new matrix which is obtained by performing the column operation. So this is the meaning of this column operation. Take the next example as matrix A equal to 1, 2, minus 1, 0, 1, 3. On this matrix, we have to perform the column operation 2, C2. That means each element of the second column, you have to multiply a non-zero scalar 2. And you are given the matrix B as 1, 0, 2, 2, 4, 5. You have to perform the row operation minus 3 into R1. That means each element of the first row, you have to multiply a non-zero scalar minus 3. And then you have to take the addition of those new matrices 3. So this is the new matrix A. Then take the matrix B as 1, 0, 2, 2, 4, 5. Now we consider the row operation. So minus 3 into R1. So matrix B is equivalent to new matrix B. So the elements of first row is obtained by multiplying minus 3 to each element of the first row. So minus 3 into 1. Then again minus 3 into 0. So again minus 3 into 2. So no change in the second row. 2, 4, 5. So matrix B is equivalent to, so minus 3, 0, minus 6, 2, 4, 5. So now you have to take the addition of what? The new matrices. Therefore, matrix A plus matrix B. Matrix A is what? 1, 4, minus 1, 0, 2, 3, plus matrix B. What is B? Minus 3, 0, minus 6, 2, 4, 5. Take the addition of these two matrices, which is obtained by adding the corresponding elements of both the matrices. So 1 plus of minus 3, second with second. So 4, 4 plus 0, third with third. So minus 1 plus minus 6, then 0 plus 2, that is 2 plus 4, that is 3 plus 5, further equal to, so 1 plus of minus 3 is 1 minus 3, 4 plus 0 is 4, minus 1 plus minus 6 is 1 minus 6, then 0 plus 2 is 2, 2 plus 4 is 6, 3 plus 5 is what? 8. So therefore, matrix A plus B is equal to 1 minus 3 is minus 2. So this is 4, minus 1 minus 6 is minus 7, 2, 6, 8. So this is the solution of this example. Take the next example. Use suitable transformation on the matrix 1, 2, 3, 4 to convert it into an upper triangular matrix. What do you mean by upper triangular matrix? A square matrix in which all the elements below the principal diagonal are what? 0. So that is known as the upper triangular matrix. This is in case of what? 2 by 2. So if I consider one more matrix, say 3 by 3, say 1, 2, 3, 0, 4, 5, 0, 0, 6. So all the elements below the principal diagonal, below the principal diagonal, if all the elements are 0, then this matrix is known as what? A upper triangular matrix. Here you get a matrix in the form of a triangle, upper triangular matrix. So now you have to convert this in terms of upper triangular matrix means what? You have to make this element 0 by performing either by performing the row operation or by performing the column operation. So let us perform the row operation as a R2 tends to R2 minus 3 times R1. So matrix A is equivalent to there will be no change in the first row. We write down the first row as it is. Now change in the second row. How it is obtained? The elements of second row are obtained. Second row is 3 minus 3 into element of the first row, that is 1. Then take the next element. R2 is here 4. Then minus 3 into R1. R1 is what here? 2. That is matrix A is equivalent to 1, 3 as it is, minus 3 ones are 3, 2 as it is, 4 minus 3 twos are 6. So matrix A is equivalent to 1, 3 minus 3 is what? 0, 2, 4 minus 6 is what? Minus 2. So here we made all the elements below the principal diagonal. This is the principal diagonal. Below all the elements are what? 0, which is nothing but what? An upper triangular matrix. So this is the solution of this example. Take the next example as convert matrix 1, minus 1, 2, 3 into an identity matrix by suitable row transformation. What is the definition of the identity matrix? A square matrix in which all the non-diagonal elements are 0 and every diagonal element is equal to what? 1. And the identity matrix is denoted by a letter I. So for example, matrix I equal to 1, 0, 0, 1. So all the non-diagonal elements are 0, every diagonal element is equal to 1. Or if I consider in terms of 3 by 3 matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. So all the non-diagonal elements are 0 and every diagonal element is equal to 1 is known as the identity matrix. So the given matrix is 1, minus 1, 2, 3. So first we make this element 0. How? By subtracting 2 from 2. If I subtract 2 from these 2, you will get 0. So R2 tends to R2 minus 2 times R1. So matrix A equal to no change in the first row, 1 minus 1. Second element of second row is 2 here, minus 2 into R1. R1 is 1. Then again R2 is here 3 minus 2 into R1. R1 is minus 1. No. Then the next step, first row as it is 1 minus 1, 2 as it is, 2 into 1 is 2. So 3 as it is, minus 2 into minus 1 is plus 2. So 1 minus 1, 2 minus 2 is 0. So 3 plus 2 is what? 5. So we made this element 0. Now we have to make this element 0. So first I will make this element what? 1 by dividing the same element. So 1 upon 5 into R2. So matrix A is equivalent to 1 minus 1. 1 upon 5 into 0. Then 1 upon 5 into 5. So that is 1 minus 1 as it is. 1 upon 5 into 0, 0. 1 upon 5 into 5 is 1. Then we made this element 1. Now it is required to make this element 0 by taking the addition of these two. So R1 tends to R1 plus R2. So R1 is here 1 plus R2 is 0. Next R1 is here minus 1 plus R2 is here 1. No change in the second row. So 1 plus 1, 0 is 1. Minus 1 plus 1 is 0. 0, 1. So all the elements, all the non-diagonal elements are 0 and every diagonal element equal to 1. So which is nothing but the identity matrix. So in today's class we have seen the elementary transformation and the examples based on the elementary transformation. If you feel that this video is really helpful for you, then you like it, share it, write your valuable comment on this video, and subscribe the channel.